Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen the different Boolean laws. The only thing which remained was the De Morgan's theorem or the De Morgan's law. So in this video, let us understand that because these laws are very useful in minimizing the Boolean expression or the Boolean functions. And first, let us see this first law. So as per this law, the complement of the a plus b is equivalent to a bar dot b bar. So if we see from the logic gate perspective, then this a plus b whole bar is equivalent to the two input OR gate followed by the NOT gate. So we know that if a and b are the input to this OR gate, then its output is equal to a plus b. And when it is passed through the NOT gate, then its output will be equal to a plus b whole bar. So basically, this NOT gate inverts the output. And we also know that this OR gate followed by the NOT gate is equivalent to the NOR gate. That means if we apply the A and B input to this NOR gate, then its output is equal to A plus B whole bar. That is equal to the left hand side. So similarly, let us see the RHS. So this A bar dot B bar is equivalent to the applying the input A bar and B bar to the AND gate. And these A bar and the B bar signals can be generated by passing this input A and B through the NOT gate. Now this circuit is often drawn in the abbreviated form like this, that is the bubbled AND gate, where this bubble at the input indicates that the input gets inverted before the AND operation. So as per this De Morgan's law, this NOR gate is equivalent to the bubbled AND gate, that is A plus B whole bar is equivalent to the A bar dot B bar. So using the truth table, now let us also prove that. So for the two inputs A and B, there are total 4 different possibilities. So first of all, let us find this A bar and the B bar. So this A bar is the complement of the A. That means when A is 0, then this A bar is equal to 1. And likewise, when this A is equal to 1, then this A bar is equal to 0. Similarly, this B bar is the complement of the B. So once we have this A bar and the B bar, then we can easily find this A bar dot B bar. So this A bar dot B bar is 1 when the both inputs A bar and B bar are 1. And when any of them is 0, then this output is equal to 0. So in this way, we got this A bar dot B bar. Alright, so now let us find this A plus B. So this A plus B is 0 when both inputs A and B are 0. And when any of them is 1, then this A plus B is equal to 1. Now this A plus B whole bar is the complement of this A plus B. So in this way, we also got this A plus B whole bar. And if you see these two columns, then we can say that this A bar dot B bar and this A plus B whole bar are same. So this law is valid even for more than 2 inputs. That means if we have 3 inputs A, B and C, then this A plus B plus C whole bar is equivalent to the A bar dot B bar dot C bar. Likewise, for the 4 inputs, this A plus B plus C plus D whole bar is equivalent to the A bar dot B bar dot C bar dot D bar. So that is the De Morgan's first law. Similarly, let us see the second law. So as per the second law, the complement of the A dot B is same as the A bar plus B bar. So first of all, let us see the same from the logic gate perspective. So this A dot B whole bar is equivalent to the AND gate followed by the NOT gate. So the output of this AND gate will be equal to A dot B, and this NOT gate inverts that output. That means the overall output of this combination is equal to A dot B whole bar. Now we know that this AND gate followed by the NOT gate is equivalent to the 2 input NAND gate. That means if we apply the input A and B to the NAND gate, then its output is equal to A dot B whole bar. That is equal to the left hand side. Similarly, let us see the RHS. So this A bar plus B bar is equivalent to the applying the A bar and B bar input to the OR gate. And this A bar and the B bar signals can be generated by passing the inputs A and B through the NOT gate. And as we have seen, this circuit is equivalent to the bubbled OR gate, where this bubble inverts the input before the OR operation. That means as per the second De Morgan's law, the NAND gate is equivalent to the bubbled OR gate. So now let us prove the same using the truth table. And first of all, let us find this A bar and the B bar. So as we have seen, these A bar and the B bar are the complement of the inputs A and B. So once we have this A bar and B bar, then we can easily find this A bar plus B bar. So this A bar plus B bar is low when both inputs are low, and when any of the input is high, then this A bar plus B bar is high. So in this way, we got this A bar plus B bar. Similarly, to find this A dot B whole bar, first of all let us find this A dot B. So this A dot B is high when both inputs A and B are high, and when any of them is 0, then this output A dot B will be equal to 0. And this A dot B whole bar is the complement of this AB. So now, if you see these two columns, then we can say that this A dot B whole bar is equivalent to the A bar plus B bar. So this law is also valid for more than 2 inputs. That means for the 3 inputs, we can say that this A dot B dot C whole bar is equivalent to the A bar plus B bar plus C bar. Similarly, for the 4 inputs, this A dot B dot C dot D whole bar is equivalent to the A bar plus B bar plus C bar plus D bar. So that is the De Morgan's second law. So now these two laws are very useful in minimizing the Boolean expressions. So basically in these two laws, what we are doing, we are breaking this negation or the bar and we are giving it to the individual variable or the group. And at the same time, we are also changing the sign. That means here we have a OR operation and it will get converted into the AND operation. And the same thing is happening in the second law. So basically we are breaking this bar and we are giving it to the individual variable or the group underneath. And then we are also changing this sign. That means here this AND operation gets converted into the OR operation. And the same rule is also applicable to the Boolean expressions which has this sort of negation. So let us take few examples related to Boolean algebra where we can use this De Morgan's law. So this is our first example. So as you can see, this expression has a bar on top of it. So what we will do, we will break this bar and we will give it to the individual variable or the group, and then we will change the sign. So first of all, let us break this bar and give it to the individual group. That means this A will become A bar and this B bar C will have a bar on top of it. Moreover, we will also change this sign. That means now this OR operation will get converted into the AND operation. That means now we will have this A bar dot this B bar C whole bar. So once again, now let us break this bar. So now we will have this A bar dot B double bar and this C will become C bar. Moreover, this AND operation between this B bar and C will get converted into the OR operation. That means now we will have this A bar dot this B double bar or B plus C bar, because we know that the complement of the A bar is equal to A. That means this B double bar is equivalent to the B. So in this way, this A plus B bar dot C whole bar will become A bar dot B plus C bar. So in this way, using the De Morgan's law, we can simplify the expression. Similarly, let us take the second example. So in this example also, we will follow the same procedure. That means first, we will break this bar and we will give it to the individual group. That means this A plus C can be written as this A plus C whole bar. Likewise, this A plus B bar can be written as A plus B bar whole bar. Likewise, we will have this A bar plus B plus C bar whole bar. Moreover, these AND operations will get converted into the OR operations. Now once again, let us break this bar and let us give it to the individual variable. So we can write this A plus C whole bar as A bar dot C bar. So basically, we have given this bar to the individual variable and this OR operation got converted into the AND operation. Likewise, this a plus b bar whole bar can be written as a bar dot b because this b double bar is equal to b. And likewise, this a bar plus b plus c bar whole bar can be written as a double bar dot b bar dot c double bar. So once again, we have given this bar to the individual variable and we have also changed this sign. That means now we can write this expression as a bar dot c bar plus a bar dot b plus a dot b bar dot c. So in this way, using this De Morgan's law, we can simplify the expression. So similarly, let us take one more example. So in this example, using this De Morgan's law, let us simplify this Boolean expression. So as you can see over here, this expression in the bracket has a bar on top of it. So in this bracket, we will apply the De Morgan's law and then we will simplify this expression. So first of all, let us write down the remaining expression as it is, that is equal to a dot b plus c bar. Now in the bracket, what we will do? We will give the bar to the each group and then we will change the sign. That means we can write this bracket as a dot b whole bar dot complement of the ac bar. Now once again, here we can apply the De Morgan's law. So we can write this expression as a dot b plus c bar and this a dot b whole bar can be written as a bar plus b bar. Likewise, the complement of the AC bar can be written as a bar plus c. So basically, we have broken this bar and we had given to the individual variable, and at the same time, we have also changed the sign. So as you can see, further we cannot apply the De Morgan's law, but using the other Boolean algebra laws, we can simplify this expression. So let us do that. So now we can write this expression as a dot b plus c bar, and in the bracket we will have a 4 terms, that is a bar dot a bar plus a bar dot c plus b bar dot a bar plus b bar dot c. So we know that this a bar dot a bar is equal to a bar. Moreover, this b bar dot a bar is equivalent to the a bar dot b bar. So now we can write this expression as a dot b plus c bar, and in the bracket we will have a bar plus a bar c plus a bar dot b bar plus b bar dot c. So now in these 3 terms we can take this a bar common. So now we can write this expression as a dot b plus c bar, and in the bracket when we take this a bar common, then we will have 1 plus c plus b bar, and this b bar plus c will remain as it is. Now we know that 1 plus something is equal to 1. That means this entire term will be equal to 1. So now we can write this expression as a dot b plus c bar, and in the bracket this a bar dot 1 plus b bar dot c. So further if we simplify it, then we can write it as a dot b plus c bar, and in the bracket we will have a bar plus b bar dot c. So now using the distributive law, we can further simplify this expression, that is equal to a dot b plus this c bar dot a bar plus b bar dot c bar. Now we know that this a dot a bar is equal to 0. Similarly over here, this c dot c bar will become 0. That means this term will become 0. That means now we will have this a dot b plus a bar dot c bar. And once again, using the distributive law, we can write it as a dot b plus a dot a bar dot c bar, And once again, this a dot a bar will become 0. That means this term will also become 0. And at the end, we will have ab. That means this entire term is equivalent to ab. So in this way, using the De Morgan's law, we can simplify the Boolean expression. Alright, so this is the fourth example for your exercise. So using the De Morgan's law, try to simplify this expression and do let me know your answer in the comments. But I hope in this video, you understood about the De Morgan's law. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.